all halogens react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. We see here, these all are HCl HBr HI. The affinity for this hydrogen decreases down the group because of reduction in electron activity. The stability of these halides decreases down the group as well due to decrease in bond strength as HX bond length increases down the group, so that the bond dissociation energy reduces. The reduced bond dissociation energy results in lower stability of these compounds. Now, acidity of haloacids. The acidic strength depends on the ability to furnish protons. As HI bond dissociation energy is small, it easily breaks to give us proton. So, going from HI to HF, bond dissociation energy reduces as we go from HI to HF, from HF to HI, and that's why acidic strength will increase from HF to HI. HI is the strongest, HF will be the weakest acid. It's clear here, pKa, smaller the value of pKa, larger will be its acidity. It's -10, so it is the strongest acid among all these. Now, melting and boiling points. HF having a high melting point compared to HCl due to hydrogen bonding. But as we go from HCl onwards, the melting point keep on increasing, as we can see here, 159, 185 Kelvin, 222 Kelvin. The reason for this enhanced melting points is, as we go down the group, size of that anion or halide increases, so do the intermolecular van der Waals forces of attraction, which depend upon the atomic size. That is the reason we are getting a higher melting points as we go down the group. HI having the highest, and this is HI, and looks in a solid state. This is the reason HI have highest boiling point among all the halides. Now, oxides of halogens. ClO2, chlorine oxide like Cl2O, chlorine dioxide, Cl2O6, Cl2O7 are highly reactive oxidizing agents and tend to explode. They are very strongly oxidizing, and chlorine dioxide is used in industry as a bleaching agent. It is used in paper industry, pulp and textiles, and for the water treatment as well. Here we see this is a pulp that used for paper making, but it's supposed to be decolorized first, bleached first. So a pulp is treated with this ClO2 and we get a white pulp which is ready for making paper. Further, we having chlorine production using CaO Cl2, this compound. It under acidic conditions gives us hypochlorous acid, which further decomposes to give a chlorine, nascent oxygen and water. This nascent oxygen will act as a bleaching agent. Further, oxides of bromine are least stable among the halogen oxides. So if you have to see the stability point of view, bromine oxides are the least stable metal halides. For monovalent metal, the ionic character of the halide decreases in the order from this is metal fluoride is greater than metal chloride, greater than metal bromide, greater than metal iodide. So as from going from fluoride to iodide, we see ionic character reduces. This fits well according to Phosgene's rule. Larger the size of anion, smaller the size of cation, covalent character will increase in that case. For a metal exhibit more than one oxidation state, the halide in the higher oxidation state will be more covalent other than one in the lower oxidation state. This is again according to Phosgene's rule. For the same reason, UF6 will be more covalent than UF4. Tin tetrachloride will be more covalent than tin dichloride. Lead tetrachloride will be more covalent than lead dichloride. Antimony pentachloride will be more covalent than antimony trichloride. The reason is same Phosgene's rule. Here, it is all here anions will be same, only cations are different in different oxidation state. It is uranium will be 6 positive, which is more polarizing than 4 positive uranium. UF4 and UF6 structures. This is more covalent than UF4. Chlorine. Chlorine is a greenish yellow gas with a pungent smell, suffocating odor, and 2 to 5 times denser than air. It is prepared using electrolysis process. Electrolyting, we use electrolysis here of sodium chloride solution. Also, many times molten sodium chloride is used. Chlorine is liberated at anode, while sodium will be liberated at cathode. You see here, chlorine is going here. Here we use a molten sodium chloride. Sodium is coming out here. Graphite is used as anode and cathode is steel cylinder. Now, Deacon's process. What is the Deacon's process of chlorine production? In this, we oxidizes HCl in presence of copper dichloride catalyst at nearly, you can say 450 degrees Celsius temperature, 7 to 23 Kelvin. In presence of oxygen and catalyst copper dichloride, we are getting chlorine coming out and water. Chlorine too having a bleaching action as you saw earlier, and its bleaching action is due to oxidation. We have a stainless cloth here. If we are adding a bleaching agent that releases chlorine, what happens? It reacts with water to give us HCl as well as nascent oxygen. This nascent oxygen is having a very strong oxidizing power. It oxidizes the organic material present. So, stain will be gone. Colorless substance will get, stain is gone. Not chlorine directly we should say, but chlorine generated nascent oxygen is responsible for the bleaching action. Chemical reactivity of chlorine, depending on which reagent is in excess product can differ greatly. Where here, let's say we are passing chlorine through ammonia. If we are having ammonia in excess, then we are getting ammonium chloride and liberation of nitrogen. So here we are having ammonia in excess, but let's say the condition is reverse. Chlorine is in excess, then what happens? We are getting NCl3, nitrogen trichloride, which is explosive in nature. So depending upon which reagent is in excess, we can getting a different product. Ammonia, we are getting ammonium chloride. Chlorine, we are getting NCl3. Reaction of chlorine with alkalis at different temperatures. Let's say we are reacting sodium hydroxide add with chlorine under cold conditions, getting NaCl, NaOCl, sodium hypochlorite chlorus plus H2O. This is sodium hypochlorite we are getting. In the hot condition, when we concentrate the solution in sodium hydroxide reacts with chlorine to give a NaClO3, which is chlorate. Here we are getting hypochlorite. So depending upon the condition, temperatures also, we can get different products. If we react dry calcium hydroxide with chlorine, which is a powder known as lime, if we pass through this powder chlorine gas, we are getting a bleaching powder, ClO Cl2, you just saw earlier. Now oxidation reactions of chlorine. Chlorine oxidizes sulfur dioxide to sulfuric acid in presence in aqueous solutions. Sulfide to sulfates again, where it's a strong oxidizing agent, reduce itself. It oxidizes iodine to iodic acid. Iodine got oxidized to iodic acid, and further ferrous to ferric in the presence of acidic condition, H2SO4. We are getting ferric ions. Chlorine is used in preparation of multiple products like 2-chloro benzylamino, which is nothing but tear gas used for crowd control. It is used as a CCl3 nitrate. This nitrite known as a herbicide. Mustard gas, which is a chemical weapon. It was used on multiple occasions in different parts of the world. Phosgene is extremely poisonous, CuCl2. Next, chlorine is used in photochemistry as well. In organic reactions, it is used to chlorinate hydrocarbons. Depending upon the bond energy, reaction will take place at different temperatures or in the presence of radiation. Let's see, we are having alkanes. In presence of UV light, we are getting a complex mixture of isomeric mono or poly haloalkanes, which are difficult to separate obviously. These reactions proceed through free radical mechanism. UV light got enough energy to break these CH bonds. So when we pass this light, what happens? Methane got chloromethane, dichloromethane, trichloromethane, tetrachloromethane. Within all these compounds mixture is there. So we having all these 5 HCl plus 4 these possible compounds plus methane as well. As it is, so all these compounds present will make it very difficult to separate all these compounds. This chlorination is not selective. Ethene, which is unsaturated hydrocarbon, it got pi electrons. So these pi electrons can nucleophilically attack chlorine, one of the chlorine atom in a molecule. It attacks this position, and we are getting substituted chlorine here. Addition chlorine, 2 chlorine atoms are added to the pi bonds. Aqua Regia. What is Aqua Regia first? Aqua Regia is a mixture of concentrated HCl and concentrated nitric acid in ratio of 3 to 1 that is used to dissolve noble metals like gold and platinum. So far we know gold and platinum exist in pure form in nature, and in pure form they do not react with any acid or alkali. But if we mix HCl and nitric acid in right proportion, that is HCl to nitric acid in 3 to 1 ratio, we are getting such a mixture known as Aqua Regia that can dissolve the noble metals. First, gold. What happens? It oxidizes the gold to 3 positive state. Then chloride from HCl complexes with gold to give us a tetrachloroaurate. In platinum, what happens? First is converted into hexachloroplatinate. So in this way, we are getting a solution of these noble metals.